Okay, 2012 AMC. This is AMC12A Problem 25, the last one, and probably going to be the most confusing video that I've put up so far. But hey, let's get right into it. So let f of x equal the absolute value of 2 times the fractional part of x minus 1, where that denotes fractional part of x. The number n is the smallest positive integer such that the equation n times f of the quantity x times f of x equals x has at least 2012 real solutions. What is n? And note the fractional part of x is a real number, y equals x, blah blah blah. We know what this means. Like, you take out every whole integer and you're left with the decimal remainder. Okay, you modulo 1. Okay, so all right. And the first time I looked at this problem, I was like, how the heck am I going to solve an equation with 2012 solutions? But that's not the problem. Here's the first thing to notice. Okay, so this fractional part of x is strictly between 0 and 1. Okay, and actually it's strictly less than 1 based on this definition, which means that 2 times this is between 0 and 2 minus 1. So here, let me show all of it. 0 is less than or equal to 2 times this fractional part of x is less than 1. Whoa, no, not the 1. I said 2 because it is twice. That minus 1 is between, then, of course, negative 1 and 2. It's not 2 and 1. We subtracted 1 from everything. And the absolute value of this, because it is strictly between negative 1 and 1, it is bounded by negative 1 and 1. The biggest magnitude I can get to is a magnitude of 1. So the absolute value of 2x minus 1 has to be less than or equal to 1. And that's the big aha moment, because now this right here tells me that n multiplied to this means that I will only get solutions for this. So I know it has to be positive when 0 less than or equal to x less than or equal to n. This is the only possibility. So n acts like this limiter, cutting off when I can get solutions for this equation. And in the effort to actually have room to explain this, let me erase this. Alright, I hope you didn't need it. Okay, erase, erase, erase. Alright, so now let's look at this. Let's look at the function. Let's see what happens. I'm going to explain this by sketching the graph of it, just so we can see what happens. So, and I'm only going to care about positives because we can only get positives out of here. So here we go. So f of x, and I'll explain why this has to be the case and how we can figure it out without graphing it. So when x is 0, we know we get to 1, but as x gets closer to 0.5, 2 times that gets closer to 1, 1 minus 1 gets closer to 0. So as x gets closer to a half, we get closer to 0. And then we go back as x gets closer to 1, then we get closer to 2 minus 1, and the absolute value of that is 1. And this continues because we're looking at the fractional part, so it's all mod 1 here. So I repeat this over and over. Okay, that's f of x. Next thing we're going to see is x times f of x Okay, so let me give myself a little bit more room. Okay, so x, the identity line x, looks like, and we know that f of x is bounded between 0 and 1 and actually reaches 1. So what's going to happen is my curve here will be bounded between 0 and x, and it'll have the same basic shape, but it'll be a little bit curved. So this is going to be the graph of x, f of x. So we get this shape. We hit the 0 when we get the 0 here, and then we go up to 1 over here, and they're curved. They're not straight anymore, but it doesn't really matter. So we get this shape. We go up to 2 times 1, which is x times 1 here. We go up to 3 times 1. We go up to 4 times 1. Okay, so we have... All right. Okay, so that is what f of x looks like. They're curved, it continues on in this pattern. But when I take f times that, okay, so this is where we're finally getting to the interesting part. And it is going to be bound on the top by n. So let me just put an n up here, okay? When I take at the function of this, basically here's the gist. Every time I'm close to a whole number, or I reach a whole number, I get 0. Every time, oh no, sorry, I get 1. Every time I get close to a half, I'm going to mark them off here so we can see them and count them. Every time I get close to a half, well, f of something whose fractional part is a half will be 0. So every time I hit this, I get to a 0. So we can see, and I'm multiplying it by n, so I'm going to go straight to n f of x, f of x. Okay? And so I start, x f of x starts off at 0, means f of that starts off at 1, so n, it starts off at 1. Let me a little bit more. Okay. All right. So it starts off at 1, but you can see it barely gets up there. It doesn't really break maybe a quarter. I didn't do the calculations, but it's not really getting close. Between 0 and 0.5. So we don't actually get closer than maybe half of n. Between 0 and 0.5. Let me do this better. Okay, so, but then between 0.5 and 1, I hit a 0.5 here, so I come down to 0 and get back up to n. Between 1 and 1.5, I go down to 0 and go back up to 1 once. So 0, back up to 1 once. And then I go 0, 1, 0, 1 twice. Oh, this is going to be a pain to try to show it. It gets messy very quickly. So 0, 1, so 0n, 0n. Okay, and so let's see. Let me do it one more time. So this next thing from 2 to 3 goes 0, 1, 0, 1 twice. So 0, 1, 0, 1. And then it goes 0, 1, 0, 1, 0, 1. Okay, so it hits that 3 times. 0, 1, 0. 0, 1, 0, 1, 0, 1. Okay, and any one of your graphers will do the same thing, but here's the idea. I want to solve where this equals x. So I have some line, and to figure out how often I go through this, that's what the n does, but basically, here's the idea. Between 0 and 1, you can see that the blue curve and the yellow curve intersect twice, meaning this equation has 2 solutions between 0 and 1, as long as n is big enough. And between 1 and 2, I get 2, 4, 6 solutions. And let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's hard to see them, but between 2 and 3, I get 10 solutions. And you can see that in here by how many times it oscillates back and forth, and so forth and so on. Okay? So I actually get now the sum as k goes from, let's say, 0 to, let's do 1 to n of, and if I wanted to write this, I could write this. So we see that we have a 4k. So each step forward, each time n goes up by 1, I will get 4k more, 4n more terms out of that. But to get the first one correctly, I will have minus 2. Okay? And this is going to, so it's going to be 2 plus 6 plus all the way up to 4n minus 2. And this is an arithmetic sequence with common difference 4. I have n terms. So, and we've seen this before, I add the first and last term, the second and the second to last term. So I add them together, 4n. Multiply by the number of terms divided by 2 to get how many of those sums I will have. And 2n squared will be the number of solutions I get. But I want that 2n squared to be at least 2012. Oh, I have no room. So I want 2n squared to be greater than or equal to 2012. And so I'll divide that by 2, and I will magically rewrite it up here. So if I divide by 2, I'll get n squared is greater than or equal to 1006. Okay, and I know 30 squared, so I'm just going to do this. 30 squared is 900. We know that. 31 squared. And so I knew I was in the ballpark. That's why I started here. 31 squared is 900 plus 30 plus 31, which is going to be 961. But I'm still not there. 32 squared, 32 squared is going to be 961 plus 31, which is 992, plus 32, which gives me 224. 1024. Can that possibly be right? Yeah, okay, that's power of 2, which is bigger than 1006. So 2n squared would be bigger than 2012, so my answer is C, 32.